Hello, good morning. I'm Santosh K presenting AI-driven agent for automated threat response. Traditional security takes 4 to 6 hours to respond to attacks. We reduced that to 8 to 12 seconds using AI and SDN. Let's dive right in. Let's move on to the introduction. The problem we stated was traditional security is reactive, static firewall rules, manual alerts, isolated tools. Attacks spread while analysts investigate. Our solution proves that AI-driven SDN and NFV combines machine learning anomaly detection with centralized network control, which results in a real-time automated threat response, 40% reduction in latency, self-healing defense. Let's move on to the statement of problem. Here, the challenge we focused on the larger side was response latency of 4 to 6 hours. Why then the damage is already done? The objective of this project is to design an ASTN framework achieving less than 50 millisecond interference latency, 90% true positive rate, and 40% reduction in reduction latency from 4 to 6 hours to 8 to 12 seconds, and also autonomous containment via VLAN microsegmentation. The scope of this project is to create a SDN control layer with a REST API and machine learning models, and also VLAN microsegmentation and NFV like PFSense and Suricata. The target audience was cybersecurity professionals, SOC teams, enterprise network administrators, and critical infrastructure operators. What we included and excluded in this project was the included was a reused controller with OpenFlow 1.3, ML model development, and Flask REST API deployment with VLAN micro segmentation and performance comparison. The not included items was production deployment, only the tested only. This was done in Mininet environment. Custom OpenFlow modifications are not included. Team integration is not also included. But we are working on this for the future work. Let's get down to the methodology we use. We use a six-phase approach: data collection from OpenFlow switches, and then pre-processing and normalization of data, and ML model selection. We used four models: random forest, isolation forest, one-class SPM, LO. Model training was held with scikit-learn, and REST API deployment via Flask, which is working on Post with Port 5000, which has three endpoints like health, info, and predict for API call. And end-to-end testing and evaluation was done for accuracy, TPR and FPR and response time. Let's move to the system architecture. We have Mininet plus OpenSwitch network emulation on the bottom, and the left Ryu Exchange controller with OpenFlow control. On the middle, we have Flask AAP with random forest model, which is the best model we choose for. And on the right, we have VNF services like PFSense, Firewall, Suricata IDE. The flow starts from traffic to switch to AA API to decision and drop rule or allow rule. And on the drop rule, we have VLAN microsegmentation like isolation. Then the use case diagram, we know that it has acted network security administrator and use cases like configure SDN controller, monitor flow statistics, trigger AI model training, and detect anomalous traffic and apply containment policies. These two are automatic. We alerts and logs on anomalies, the performance matrix, etc. The design class states that key classes like anomaly detection trainer, AI anomaly API, and microsegmentation controller and also have network flow collector, which gathers the real statistics from the flow. Sequence diagram proves the flow arrives at the switch, the controller pulls the statistics, and extracts features like duration packets, bytes, erase size. Post to AI API. Random forest interference with 23 milliseconds. Response like attack or binning is showed on the AI API. If attack install drop rule plus VLAN segmentation, if allow, it can allow the host to pass through the switches. Log event every 8 to 12 seconds. An algorithm used was random forest, which is the winner 92.3% accuracy. and 93.1% true positive and 4.2% false positive with 50-second training time. The remaining showed poor performance. Random forest uniquely balances the accuracy plus speed. And on the implementation, we used tech stack as Python, and for web AI dashboard like Flask, RESTful, and data preprocessing, we used Pandas, NumPy, and for model training, we used Scikit-learn. For SDN, we used Ryu plus OpenFlow. For network, we used Mininet plus OpenVSwitch. For VNF, we used PFSense Suricata. Important code segments like model trainer is showed here. Instance the four models as we spoke: random forest, isolation forest, one-class SVM, and local outlier factor. Then we move on to the REST API, which collects the packet flows from the switches and makes decision according to the logic and model we choose. This is a microsegmentation controller. This is where if the AAP detects an attack, it will be showing some commands like drop or isolate so that the microsegmentation controller isolate it's in any trusted VLANs like 100, 200 or quarantine 999. These are the codes for microsegmentation. Then let's move on to the training results. Training results confusion matrix give that 71,960 true positives and 1,447 false positive and 11K false negatives. This is the confusion matrix and training time for each model. Random forest has the lowest training time with high accuracy. Random forest also showed that F1 score on 0.9 to 1. The remaining was not performed efficiently. Random forest has accuracy 0.96, precision 0.98, and recall at 0.87. The training model proves that penning traffic has 81.2% high confidence and attack traffic 18.8% successfully identified as malicious activities. F1 comparison shows that random forest has exceptional threat detection performance, confirming superiority for production deployment. The training model conclusion by F1 score and training time. Output and demonstration will be shown in another video. Thank you.
Let's move on with the deployment and demonstration process. Here we running the AAPI script to turn on the AAPI that we used for this project. And the A anomaly reduction API is run and waiting for request on port 5000 on local. Then on the other terminal, we are running the RU manager in which we have the RU controller set up, a custom made for this. And the thread is started and waiting for switch to connect. And on the next terminal, we are going to run the mininet topology on the localhost IP 127.0.0.1 with port 6633, which OVS open virtual space. And the topology is created with H1, H2, H3 and switch 1 and all links connected to it. And we have a virtual VNF host and VNF IDS host. Now when we look back into the view controller manager, switching is connected now. Then a flood attack is planned to be posted in the mainnet. From H1, a flood attack on this port 80 with synchronization flare. Now the flood mode is active. And when we look into the view manager from 192.168.10 to 192.168.11 on the port 80, heuristic DOS attack is detected and it is blocked. Okay. I forgot to turn on the dashboard. Python 3. And the dashboard shows the A detection API is online, exchange control is online, and VNAV services are online. And, and shows that the flow analyzed as benign from the beginning and the thread detected as DDoS. Like we said like this, and we look into the A API. Only the benign health status from the dashboard is showcasing here because every DOS flood is blocked by the review controller, and it is mentioned here. And in the dashboard, the host is quarantined also. Then we move on to the next. Then we move on to the next test case. When you try the same flood with UDP protocol, the flood is finally done. This one is waiting for the flow to be corrected by review controller. And here is what the DOS attack is again actually detected and blocked the. Now it's 120 because you're trying from H3. H3's IP is 192.168.120. On the previous test, we done this with 1.10, which is H1. Now it's blocked, and the only benign attack will be shown in the API. There is no flow detected because the flow is blocked. You can see it in the bottom. There is no flow detected because the flow is blocked by a controller, like this. This is the result of this demonstration.